Welcome to the Generative AI Theory tutorial series. Today, we unravel Variational Autoencoders, or VAEs, a cornerstone of deep generative modeling. Variational aspect comes from regularizing the latent space. We want the learned latent distributions to conform to a simple prior, usually a standard normal distribution. Different inputs might map to distinct, disconnected regions in the latent space. This creates holes where random sampling fails. A continuous and smooth latent space allows us to interpolate between points, generating gradual transitions between data samples, a hallmark of VAEs. This regularization is achieved using the Kullback-Leibler, or KL-Divergence, which measures the difference between two probability distributions. In VAEs, we minimize the KL-divergence between the distribution learned by the encoder, Q of zx, and our desired prior, P of z, typically n of 0, 1. For Gaussian distributions, the KL-divergence simplifies. It pushes the mean of the learned distribution towards 0 and its variance towards 1. The mu-square term directly penalizes the deviation of the learned mean from the prior's mean, which is 0. This centers our latent distributions. The variance term encourages the learned variance to approach 1, balancing reconstruction with regularization. Too small, and the space is restrictive. Too large, and it becomes noisy. The KL-divergence term ensures that the latent space is continuous, well-behaved, and allows for meaningful sampling and interpolation. A challenge backpropagating through the sampling step, n of mu, sigma squared, is problematic because sampling is a non-differentiable operation. Recall standard autoencoders, they learn an efficient data representation by encoding inputs into a latent vector, then decoding back to reconstruct the original. The Reparameterization trick elegantly solves this. Instead of sampling directly, we express z as a deterministic function of mu, sigma, and a random variable, epsilon. Here, epsilon is sampled from a fixed standard normal distribution, external to the network's trainable parameters. This makes z differentiable with respect to mu and c. Now, the gradient can flow seamlessly through the deterministic operations to update the encoder's parameters for mu and sigma. Think of it like this. Instead of randomly picking a point on a ruler, you randomly pick a mark on a standard ruler, then scale and shift it to your desired measurement. This trick is vital for training VAEs effectively. It allows for the simultaneous optimization of both reconstruction and regularization losses via gradient descent. Once trained, generating new data with a VAE is straightforward. Simply sample a latent vector z directly from the prior distribution, n of 0, 1. Because the latent space is regularized, any sample from our n01 prior will map to a meaningful and coherent output through the decoder. This generative capability makes VAEs powerful for tasks like data augmentation, anomaly detection, and creating novel yet plausible content. Many extensions exist. Conditional VAEs for controlled generation, disentangled VAEs for interpretable latent dimensions, and more advanced architectures. VAEs merge an encoder-decoder structure with a probabilistic approach, ensuring a structured latent space for meaningful generation. The KL-Divergence and Reparameterization trick are key. However, standard AEs lack a structured latent space. Sampling from it to generate new data often yields meaningless outputs. Thank you for joining this deep dive into VAEs. Continue your journey into generative AI with other tutorials in our ArcTech series. Until next time, VAEs address this by making the encoder probabilistic. Instead of a single latent vector, it outputs parameters defining a distribution in the latent space. For each input, the VA learns a unique Gaussian distribution within the latent space characterized by its mean and variance. A latent vector z is then sampled from this distribution. This z is fed into the decoder to reconstruct the original input. The VAE's objective function has two crucial components, reconstruction loss and the KL-divergence term. Reconstruction loss, often mean-squared error or binary cross-entropy, quantifies how accurately the decoded output matches the original input. Minimizing this loss ensures the VAE can generate outputs that are perceptually similar to the data it was trained on.